All right, welcome back. So, let's continue with our lecture from here. So, today we will talk about um, why number of how number of bonding to create a surface is different for different crystallographic planes. So 110, 100, 1, they all have different number of bondings per unit area, and that makes it that's what makes surface energy different for them. Okay, so when you think of FCC crystal, you have FCC crystal like this, like this. Then when you look at 100, let's go with the easiest one. It looks like this, right? Then there is two atoms per unit area, right? This is how many atoms you have per unit area, okay? And now you have to think about how many bonds you need to cut per atom, bondings per atom, bondings per atom. Sorry. Then when you look at 100, we drew this before, like it's like this on the second plane on the B. So A, B, A. It's another A. So you cut here. This is where you cut it. And sorry, doesn't look like this. You cut here. So when you look at this atom, there is 4 bondings. So you need to cut 4 bondings per atoms. Now remember, we normalize this by 2 because after you cut it, you will create 2 planes, 2 surface, this A surface and this B surface. So surface energy is work you need to create area, but now you have 2 areas, right? So you need to have, like, you need half the work for creating 1 area, right? You have 2 area now, so you divide work by 2. So here you can just think of it like you're cutting 2 bondings per atom. Actually, it's the same concept as, remember this, I drew this in the last lecture, and for this atom you only had to cut once. So same concept here. Okay, then it's 4 bondings per atom, divide by 2 times number of atoms per area times energy of 1 single bonding. This will be gamma, surface energy. See, you can see that if you do it, then it will be, this has a unit of bond energy per bonding, right? Joule per bonding. Then you can see this is meter squared. It will have joule per. So this is how you calculate it. Number of bondings per atom times number of atoms per area times energy per bonding times half. This is surface energy. Surface energy. This is how you calculate it. So for 111, I'll do 111 for you, and you can do 100 for yourself. Okay? Then it will look something like this, right? So if you learned stacking, if you learned crystallography, you would know that this is how you stack in this direction, in a diagonal direction. This is how you stack. So this is the key point here. Here is the body center of this cube is not included on 111 plane. Not included in 111 plane. This is very important. It will be very handy to know this when you learn crystallography. Anyway, when you stuck in this 111 direction, this is so this plane is perpendicular to 111 direction. This is 111 plane. Then you stack it like this. And here too. You stack it like this. Then you can see if this is how you stack in 111 direction, and if you had FCC, which has 4 atoms per basis, right? 4 atoms per basis. Let me think about it. Yes, 4 atoms per basis, because here you have 4 atoms per basis, like this. 1, 2, 3, and you have 4 atoms per basis. Yes. So this is one lattice point, and it will have atoms here for FCC. So like this. So if you take this part out, so this atom, you see this is the same concept. So body center is not included in 111 plane. So you stack this on top of this plane. So it will not look like this. Mind this, okay? It won't look like this. It will look like this on the bottom plane. This is lattice points. These are lattice points. These are bases. So these, of course, there is another one on top, which is the included in the basis. But anyway, this is one lattice point. Okay. And then, anyway, this plane, 111 plane, will look like this. So how many atoms per unit area? You only count here, right? Here. So as you add these 3, it's half times 4. so equals to 2. 2 divided by unit area, and you can easily see this is root 2a0, and also root 2a0, so this they're all three of them is root 2a0. Then you can easily calculate the area for this triangle, which is, so this is 60 degree, then root 2, this is 2a0, then this is this, then root 2a0 times root 6 over 2 times a0 times half, which will be 2 0 squared, which will be, what is it? 4 over root 3a0 squared. Now this is the number of atoms per unit area. Now the rest is very easy. Oh, I forgot the number of bondings you need to cut. Then this one is also tricky, so I'll also do this for you. Then if you look at here, you can see that okay, let's draw this. Just draw another one. So we all know that 111 in 111 FCC in 111 direction is ABC staking. So this will be B. A will look like this. This is A. So you can see that for this one in the center, if you try to cut through here, then of course you have to cut 3 atoms, right? So 3 3 bondings. 3 bondings per atom times 4 over root 3a0 squared divided by half. Remember this, right? Because this plane and this plane, you create 2 planes, right? Times epsilon. And then you'll get the surface energy for 111. And if you compare surface energy of 111 and 100, you'll realize that it is 1 over 1.154. So if you plug 2 for ZNA, that's equal to this, right? You'll get this. So you can see that, and also if you calculate surface energy of 100, then you'll realize 110. You'll realize 111 is smaller than gamma 110, which is smaller than gamma 100. So this is the least stable one. Why don't you guys calculate this, all 3 of these, and number of broken bonds per unit area until our next lecture. I'll show you the answer table like this in the next lecture. And number of Yeah, some kind of table like this. Why don't you guys organize all these answers, try to make a table, and I'll show you the answer in the next lecture. Okay? But the conclusion is this. All right. Thank you.